Hello and welcome to Problem 15 in my Calculus 3 or Multivariable Calculus problem solving series. In this video, we're going to look at how to switch the order of integration for double integrals. So let's look at how to switch the order of integration for double integrals. So if we have a surface f of x comma y, which equals 2x plus 3y squared, and we want to take the double integral for this region, this rectangle, which has the side length along the x-axis is 1 and this side is 2. We want to find the double integral for this region. So we need to first define our bounds. So the bounds on x will range from 0 from here to here. So the bounds on x will be constant for this example. So 0 to 1. And our y, so if these are our bounds on x, then our y is going to range from this line, which is y equals 0, to this line, which is y equals 2x. Y equals 2x. So our y is going to range from 0 to 2x. And so our double integral will look something like this, where on the outside we have our bounds, constant bounds for our x. So we're going to first integrate y. And on the inside you have our surface, 2x plus 3y squared dy dx. But let's say we want to switch the order of integration. What this means is that we're going to first integrate x and then y. So we're going to have dx dy. So if we want to do that, then we need to redefine our bounds. So to do that, we're going to write, instead of x having the constants, we're going to have y have the constants. So y is going to range from 0 to 2. Y is going to range from 0 to 2. And you can sort of imagine this as, imagine writing the bounds for your region as having 4 different curves or lines in this case. So y, the line y equals 0 and the line y equals 2. And that means that the bounds on x will be this line and this line. And those are x equals y over 2. So x equals y over 2 and it goes all the way to x equals 1. And remember that you write, in this case, since y over 2 is to the left, then you write it to the left in this equation like this, in this inequality. And so now we can redefine our double integral and write that y is from 0 to 2 and x is from y over 2 to 1. And we still have the same surface, 2x plus 3y squared, but now we have dx dy. And these two double integrals should equal the same thing because you're taking the double integral over the same region. So they mean the same thing. So let's go ahead and calculate these double integrals and see what they give us. And the first one that we're going to look at is the dy dx integral. So this is the double integral from 0 to 1 for x and 0 to 2x for y. And then it turns into the integral from 0 to 1 of 2x times y plus y cubed, evaluated from 0 to 2x dx. Then we turn this into the integral of 4x squared plus 8x cubed dx. And then when we evaluate it, we have 4 over 3x cubed plus 8 over 4x to the power 4 from 0 to 1, and we find that the answer gives us 10/3. So now let's go ahead and look at the second double integral and see if it gives us the same answer. So let's go ahead and look at the second double integral, which is now in the form of dx dy. So we have the integral from 0 to 2, the integral from y over 2 to 1 of 2x plus 3y squared. And then this turns into, when we evaluate the first inside integral for x, this turns into x squared plus 3y squared times x, evaluate from y over 2 to 1. And then we get this pretty long polynomial here. And when we take the integral, we get y plus y cubed minus y cubed over 12 minus 3 over 8 times y to the power 4. Evaluate it from 0 to 2. And then we get, when we finish the calculation, we get that it actually equals the same thing. So we see that both of the integrals, since they're both over the same region, they're both going to give us the same volume.